In this paper, we propose an ensemble diversity approach to supervised binary hashing, which is very useful in retrieval tasks. In large-scale image retrieval problems, we are interested in the k-nearest neighbors of a query image among the images inside the database. The exact search is very slow and we need a lot of space to store the images. For this reason, we need binary hashing. Binary hashing is a well-known approach that finds the approximate nearest neighbors of a query image very fast. First, it maps the images into the binary codes. Then, it compares the images by comparing the binary codes of them. This can be done very fast because we only need hardware operations to compute the Hamming distance between the binary codes. To map the images into the codes, we need a hash function. And a good hash function has to preserve the neighborhood. It means that it has to assign similar codes to the similar images and dissimilar codes to dissimilar images. To learn a good hash function, hashing papers define an objective function and optimize it over the parameters of the hash function. The objective function, most of the times, is very complicated and it is very difficult to optimize. The main reason is that the output of the hash function is binary and it makes the objective function non-smooth and non-differentiable. In this paper, we propose to optimize each 1-bit hash function independently from the rest. We define the objective function over 1-bit hash function, and then we optimize this objective function b times to achieve b 1-bit hash functions. This gives us several advantages: simpler optimization problems, faster training, massive parallelism, and also better accuracy in image retrieval tasks. The important question is how to make the 1-bit hash functions different from each other. If we optimize the same objective function b times, we get b identical hash functions, and it is not different from learning a single 1-bit hash function. We consider 3 different diversity mechanisms from the ensemble learning literature. Different initialization, where each hash function is initialized randomly. Different training sets, where each hash function uses a training set different from the rest of the hash functions. Different feature subsets, where each hash function is trained on a random subset of features. Our experiments show that our proposed method beats other hashing methods in different datasets in image retrieval tasks.